There we go. Okay.
Hello.
Good morning, everybody. You should be host now, Josh.
Okie doke. Can
Yeah.
everybody see my screen?
Yeah, maybe wait a minute or two because I
That's
kind
fine.
of ran late this morning, and so not everyone here's had a chance to get logged in. We got about pretty much everybody that was in this morning's class is logged in. Okay, go ahead and begin.
Okay. So today, I was going to see real quick if I could get.
Whenever I try to download lab17, it just pulls up lab12. Like when I'm on the syllabus, it's just pulling up lab12.
Works for me. That's strange.
Let me reload my page.
Okay, so
it works now.
Good. Today, we're going to be looking at hypothesis testing again because it's really important is the short version. So let's take some time to kind of look at why it's important. So this isn't a statistics class, which means we get to treat one of the things in this process as a black box. What is a black box? Well, in software terminology, you refer to parts of your software as a black box when you know it's input, you know it's output, but you don't care how it behaves. You don't care how you get the output. All you care is you feed it some stuff and you get some stuff out, and you're going to trust it to be right every single time. So the process we have, and some of these steps can be interchanged. I'll try to put the ones that can be interchanged here on the left, is we want to gather some data and we want to have a hypothesis about the data. And we want to see, is it true? Okay, well, this seems really simple, but there's a lot of subtleties to it. So that when somebody comes to you or you see on the news that according to study over some number of data at some place, it turns out that the hypothesis of something is false. Well, and if you're lucky, they'll tell you the methods, or maybe they'll put the reference down at the bottom. What you need, the skill you need to be able to do is to be able to go, well, that's surprising. Let me go see how they did this to see if someone's trying to mislead me or if they actually did the work. And the other part that you need to be able to do is you need to be able to do this process yourself. And you need to be able to do it well enough so that when somebody on the other side says, well, I don't believe you, so you can just say, okay, well, here's my work. And that should speak for itself. So this is the first step. And the next step, we need to figure out what distribution does our data look like? So why do we care what distribution our data looks like? Well, that's where the black box part comes in, because we have this thing, we have tests for our distribution. And this is our black box. We know they exist. There's a bunch of theorems out there that prove they work. They have some assumptions about our data and the distributions. And as long as those assumptions are met, we know it's going to work. And once we're done with that, we get to reject or fail to reject our hypothesis based on the test we do. So this part right here is really important. We see our data. There's a whole bunch of ways to figure out what distribution it is. Sometimes you look at the graph of your data and you say, okay, this looks normal. And I have some tests that say, is this data probably normal or not? Similarly, you have the same kind of process for a bimodal set of data. And all the data sets you can think of have tests you can perform that will tell you with some kind of confidence, is this one of these distributions or not? So this step right here is the kind of difficult one, is what distribution do we have and what kind of test do we want to use on our data based on what our distribution might look like? Because it might not be 100% normal. So you have to figure out which assumptions you have so that you can run your tests. And why do we care about doing all this? Is because when you say, hey, I gathered some data and I answered a question about it and it turns out it's not true. Well, someone's going to come to you and say, well, I need to see your work because I don't believe you. And this is the method that we use so that you can say, well, I put in the work and what I say is correct. Here's the proof. So that's kind of the motivation of why we do this stuff. You don't really need to worry about how the Shapiro-Wilk normality test works. You just need to know the assumptions and what kind of thing it would give you. So let's review a little bit. Last time, unless you've been flashy thingy, if you haven't seen Men in Black, the original, you really need to. One of the best movies of the 90s. Unless your memory's been wiped, what we had was a data set with two sets of numbers. We did a bunch of stuff and decided that the normal distribution data model provides a good fit for both of the sample sets. So that was what I was talking about. What distribution is this? Well, we decided that it's probably, both of them are probably normal. Then we use the right parameters for our normal data model to generate one new sample set based on each set. We then looked at what we had and we're asking a simple question. Are these sets different or similar? This is the $1 million question right here. So let us continue with that process. We have the data here. It should be the same one still. It looks kind of like this. So it's a CSV, two sets. I think there's 100 in here, 100 rows. And yeah, let's work with our code and see what we're doing. We're going to take our CSV. We're going to make a data frame out of it. And then we're going to take part of our data set and we're going to get the columns. So the last time I was doing tutoring, which I think is Tuesday for me, the student came in and started asking me some questions about 3 layers deep from start to finish. So the start of the problem, step 1, blah, 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 step 2, blah, 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 step 3, they were confused. So I started trying to figure out, okay, where is this student confused? And so I started asking some very simple things from step 1, and they had no idea. The reason I'm telling this story is at the end of that session, they were really thankful for what the method that I used and asked if anybody else would teach things that way. And I said, I don't really know of anybody. And that method is, what kind of thing are we talking about? So I've already told you that with pandas, we are feeding in a CSV. CSV is the type of thing that is being fed into our method here. And what we're getting out is a data frame. And a data frame is a whole bunch of nice, useful things. So my question to the class is, I'm making set 1 and set 2 out of this np.array function. The input is going to be a data frame, a particular column from a data frame. What kind of thing is a column in a data frame? That's the question. That's correct. Very good. A column in a data frame is a series. It's very important you remember that. Why? Well, if you're working with a piece of software, the reason we give things types, you could just say everything in Python, because this is true. Everything in Python is an object. At least I think that's true. And that's it. Everything is just an object. Okay, well, what does that get us? It doesn't really help us very much, because the reason we assign types to things is because different types of things have different properties. I know that a data frame has certain properties, and I know that a series has certain properties, such as, let's see, the describe function. It's really nice. And we know that the data frame has that function assigned to it. It's part of it. And we know that that's there because we know that it's a data frame. There's a reason we assign these things, and that's to help us know what kind of properties do they have. So we're going to talk about our series here. And from our series, we can now call these methods. I think these work on data frames too, but I tell you what they don't work on. They don't work on lists. They don't work on integers. I can't get the mean of an integer. I can't even get the mean of set1 if I were just to manually do it. It's built into the NumPy library. That's why it's important to know what kind of things are. Because if set1 is a list instead of a NumPy series, then I can't call this method. I have to make my own to get the mean of a list. But because it's a series, we know that it has this mean method, and it'll get us what we want. So we're going to get the series. We're going to get the mean and standard deviations for both of them. And then what we're going to do is we're going to do some random sampling. If you think back to, I don't remember, I think it was like lab17. The reason this number here is 100, well, what even is this? What is this function? What does it do? Well, the NumPy library has some random stuff. And what does it let us do? Random sampling is what it is really designed to do. And what's a random sample? Take an experiment where the outcome isn't known. I'm going to flip a coin, right? It could be heads or tails. And so I'm going to call my experiment flipping that coin 10 times. And tell me how many times it landed heads. That's one experiment. It's one sample. And I'm going to do that 100 times. So now what I'm doing is I'm sampling my random variable, which is how many times was it heads out of 10, 100 times. Here, we're doing random sampling from our normal distribution with mean of mu, standard deviation of sigma, and we're going to do this sampling 100 times. So we're going to do that for set 1, and we're going to do that for set 2. And then we're going to put that into a data frame. With the first column being the sampling from we just did here, and the second column being the sampling we just did here. All right. Now we're going to plot everything we just did. I'm going to clear my outputs, actually. Okay. So what we have, and let me get what we have in green here. This is the data from set 1. So that column of 100 entries, the stuff that is here, this is the stuff in green. And the stuff in red is this. Oops. Come on. It's here. This is the stuff in red. Now, what are the other two colors? What else is going on in our little graph? Well, we have the sampling we did. So in set one, we did some sampling to see if taking a random variable, we get data similar to what we actually observed, and that's in blue. And then in orange, we have the same thing done for set two. So set twos are collected data, assume it's normal, and do an experiment and see if what we get out of the normal sampling is similar to what we have actually observed. So the idea here is I've got two collections of data. We've made some assumptions that we think they're normal. Okay. Using the standard deviation and the mean for those two sets of data, do some random sampling. Surely they must be similar to what their data set came from. If they're not, we've made an error in some of our assumptions. But as you can see, the curves on both of these look pretty similar. So their respective random sampling set, so the green and the blue and the red and the orange, they look kind of close. But again, we go back to that step process I was talking about. You got collect your data, see what kind of distribution it has, do your black box testing, and then decide whether or not your assumption's correct. Because if we were just to say that visually, yep, they're similar, we're good. Are you sure? How sure are you? How can you prove it? I don't know, I just had a feeling. They look pretty close. Well, how close is close? It's tough to answer. But we know that these tests we have answer that question. So let us do that. And just to show that this is a random sample, we can plot it again and see it looks slightly different, but they are still at least visually similar. Okay. Oops. Here, what you can see is a box plot of the same data. So the first thing we're plotting is what's in green. So that's this here. This is what's in green, and this is what's in blue. And if you remember back to what is a box plot doing for us, well, it's a lot of those. I forget the name of it. There's 5 really common things you want to know about some data. So you've got the range, you've got the quartiles, you've got outliers if there are any. And so these two look pretty similar. They're in the, I don't know, 25 to 90-ish range. Same here. And these, the only thing that looks a little different is this gap here. But relative to the size of the entire set or the range of the data set, that's not that big. So on visual inspection, these two and these two, I mean, they look pretty close, but again, we can't use our eyeballs to prove something, but your eyeballs can tell you, they can inform your intuition of, I know what test to use because this is what the data looks like. Okay. So what test do we want to use? Well, we decided last time that using the Shapiro-Wilk normality test would work just fine. So what are we going to do now? This is where we're into hypothesis testing. So if we think back to what I was talking about earlier, about step 1, 2, 3, and 4. Step 3 is the black box test. That's this. Step 4 is, do we reject or fail to reject? Step 1, we're getting our data. Step 2, we're deciding on normal. Okay, so now the question I'm asking you guys is, what is our null hypothesis that we will either reject or fail to reject once I run this test. Because the test is no good if we're not asking the question. The tests are there to say, you gave me a threshold of power you wanted. So 10%, 5%, 1%. And so I'm saying within a 5% tolerance, because it's impossible to be 100% accurate, within a 5, 1, 10% tolerance, I'm telling you to reject the null hypothesis, or I'm telling you not to reject the null hypothesis. But what is the null hypothesis? What's the null hypothesis for what we're talking about right now, for this particular thing? Yes, very good. The null hypothesis for set 1 versus set 2, which is the cell we're looking at right here, is the data, I'm just going to say normal, but what that should say is normally distributed. So that's the null hypothesis. Okay, can somebody tell me for this one, other than Cole, appreciate your service, good job, what the null hypothesis is going to be for this test? So this is test 1, and this is test 2. What are we going to do? What's the null hypothesis here? So before we had someone answered that it's distributed evenly. It depends on what you mean by evenly. So I don't believe that. Well, let me ask you this: what do you mean by it? What is distributed evenly? So when we're talking about the first one, where the question is the data normal? The things we're going to be comparing are set 1 and the random sampling for set 1. For the second question, we're going to be comparing. Yes, so I'm assuming, so Dylan's answer is the data itself between the sets. That makes sense. If that makes sense, I believe is what you're trying to say. So yes, we're comparing set 2 and the random sampling for set 2. And then you said to see if those two are distributed evenly. I don't believe that I can really interpret that to be correct, but I think what you meant to say was question test 1, are these two datas normally distributed? Datas. And question 2 is the same question, just for different sets of data. So is the data for set 2 distributed normally? Is the null hypothesis for test 2. But that's pretty close. All right. So let's try it. Test 1. Well, we ran our test with a 5% threshold, and the test we ran said, now what does it mean when we get this number back? So we're talking about a normal distribution here. And if we think back, I can divide this into a couple parts, okay? I'm going to talk about the first quartile, second quartile, 1, 2, 3, and 4. So when I get something that is a value, whatever this is, let's say 100 to 250, can be anything. And I get something like, what's halfway between those two? So 150 and 75, so like 180. It's going to fall right here. So what does that mean? It means kind of like, the reason I'm estimating is because I don't know exactly the number, but it's between 50 and 75. I'm going to guess that this is 58 percentile, meaning that 58% of all data, so everything to the left, is less than the random one we pulled out. So what does it mean when I got something like this? So remember that the decimal, this means 0, 0.79%. What does that mean? What quartile, what's the word I'm looking for? Percentile is this in? Which part of the graph here should I shade in? So if I shade it in, so I need to shade it in the first quartile, you say. Okay, that is correct. But is that all we're going to be shading in? So the 5% point, let's say it's right here. If I get something, let's say in the first quartile, which is right here, which is, let's say it's our extreme number, that means I shade in everything to the left of it, meaning it's greater than everything that's just got shaded in. And if we're running a 5% tolerance, we just found one of the very few values that was to the right of that, meaning we would reject the null hypothesis. So either we reject it and we're wrong, and that just happens, or we reject it because this data is not normal. But what we got is something in the 79% area, which is like here. So what we shade in is everything to the left of that, and that's clearly to the left of our threshold. So we have a situation where we say your null hypothesis is not rejected, and the test says your data is normal. At least it says, you can't really say certainly, so it says probably, with a 5% room for error. Now let's run it for this one. This is the second set of data. We have in the top 15%, which is clearly to the left of our 5% area. And it's so therefore it's probably Gaussian. Now, if for some reason, and you don't really ever do this, if you want to consider everything to the left of 25%, meaning that you're going to reject the null hypothesis for 3/4 of your data, you can do that. This one's still not rejected, but this one is, because for some strange reason we decided to, when you take a normal distribution, generally anything in this area is where you kind of want to say, hey, something fishy's going on. We're saying anything in here, and this is absurd. You never ever do this. The only reason I did is to show that if you had a threshold where this was actually to the right of, then you would reject. Okay. So the reason we did all that stuff is so that we can say confidently. And how confident? It's a great question. The confidence is exactly what I'm saying here. So with a, let's call it 95% confidence, set 1 is probably normal. Same thing for set 2. What happens if I do this? Can someone explain to me in English about how confident I am about my result if I were to have this number here? Other than Cole and Dylan, we appreciate your service. What does it mean if my P is 0?
You're 100% sure.
That's correct. That would, if I were to run this, I will run it after I'm done talking, and I get a result back, I would say with 100% confidence, I can tell you that this data is normal. I'm surprised that actually ran. The tests don't work for 0 because that you can't have 100% confidence in anything. That's a theorem. So I'm sure when let's say you were writing this Shapiro-Wilk test, having an input of 0 is either an input error. It really is just an input error. So you can either feed back an error or say run it with the smallest thing that your computer can run. So it probably tests it for something super tiny. So I'm a little surprised it did that, but that's what this number means. So if I were to say 1 instead of anything, I'm essentially saying everything I tell you is a lie. I have no confidence. And when I do this, I'm saying with a 95% confidence, it's probably normal. Okay. So I spent a little more time over explaining this than maybe expected, but because we're going to be using the same steps over and over and over for that whole process of get the data, pick the distribution, run the test, see if you reject or not, we're going to be doing that a lot. So the next times it won't be so long. So similarly, the null hypothesis we were talking about before was, I'm tired of red, I'm going to change my color. Let's go that one. The null hypothesis was, is the data normal? Is it normally distributed? For what we're doing here, the null hypothesis is set 1 and it's random sampling from the same distribution. We don't know what the distribution is because this test doesn't care about that. We know from above that it's probably normal, but going into this question, all we care about is, are they from the same distribution? So the null hypothesis is going to be, are set 1 and the set 1 random sampling from the same distribution. So we're going to, we already have our data. We got our null hypothesis. We're going to run our black box test, which is man Whitney. And then it's going to tell us with a 95% confidence, should we reject the null hypothesis that we have here? So let's run it and see what it says. And we're going to do the same thing in the next cell for set 2 and its random sampling. All right. So with a 95% confidence, I can say that these are probably from the same distribution. And similarly, I can say it here. Now this data, it'll tell you here is when we talk about, for a normal distribution, I'm pointing at this. So this is 95%. If we get anything in this area, we fail to reject. If we get anything in this area, we reject. And what this said was the thing we got was in the 26th percentile. So it was like right here-ish. And this clearly falls in this area. So we fail to reject. Okay. So the null hypothesis of our set 1 and set 1s and set 2 and set 2s from the same respective distributions are both probably true. Okay. So based on that, we can say they're probably from the same distribution. Now let's check if set 1 and set 2 are significantly different or not. So we're going to run another test. What is the null hypothesis for this test? Can somebody tell me, other than the first 3 to answer? Hopefully we can get through everybody. What are we testing? What's the null hypothesis? So a null hypothesis always has to be a falsifiable question. Is this D6 fair? Is this D6 weighted? Is this coin fair? Is this coin weighted? So what are we trying to say here? It's actually on the screen. Yep, I guess that works. So mean set 1 and mean set 2. Here, I'll write it because this is an interesting point. So mean, well, actually, since I have a pen, I could do mean of set 1 and mean of set 2. And now what was put in the chat is this. Now the interesting part is what we're really asking, what the null hypothesis is, are these significantly different? So what does it mean for something to be significantly different? That's a $1 million question right there. But we don't really need to worry about that because this is not a statistics class. All we need to say is we've got a test that tells us, and this number here tells us how confident we are. So if a visual representation of this would be, we know they're normal from everything we're talking about above. If they're significantly different, well, the more significantly different they are, the further apart they're going to be. If they are significantly the same, then they'll be right on top of each other-ish. All right, so let's run our test. And it says these are probably different distributions. And this rejection is all the way at the right-hand side. So you can't infer everything from what the rejection was, but sometimes it can tell you some stuff. All we know is with a 95% confidence, these are probably different. So we did that for the data we collected. We can do the same thing for the random sampling we did. And our test tells us that for both of these, they're probably different. Okay, so I spent quite a lot of time explaining every single thing we're doing. Now it's time to do it all again for some new data. So our the other set of data is here, and we have quite a lot more of it. The only thing I can say that they have in common is that there are 2 sets in our CSV, and each one has a type of a decimal float. All right, so given that almost 40-minute long explanation of the process of hypothesis testing in Python, let's repeat it. So what shall we do first? And it's totally fine to just answer in English, and we'll go look for the code that does it. You don't have to tell me the code line, but if you want me to tell a code line, that's fine too. What's the first thing we should do? Read in CSV. Very good. So get the data file ? Are you sure? The process that we're going to be doing. So I'm a big proponent of what I call English into code. Is what we're going to be doing is read in our data. And put it into a format we like. So read in our data. How do we read in our data? All we kind of have is this link here. And let's even go a step further and say I haven't actually done that already from last time. So I have a link, and that's all I've got. So does anybody know how we might get this data file so that we can read it in and put it into a format we like? Obviously, you don't have to tell me the exact code. You can tell me where to look, or you can kind of explain how it works. Because I don't have the syntax memorized either. It's a copy and paste that we're going to find, but the question is, what do we copy and paste? Oh, well, somebody already knows how to do it. That works too. Okay, so this does quite a few things. What will happen if I hit the execute button? Yes, that technically is correct. We could, and that is the best kind of correct. We could right click and download, or we could do it through a request. What does the class want to do? If we right click and download, the only problem with that is if for some reason I've deleted my file like I just did, I can't programmatically do it, which means let's say instead of one set of data, I have 50. You don't want to right click and download 50 sets of data. Let's look at how we did it above. Okay, so above, we simply had it right clicked and download. I'm totally fine with going about doing this. Just know that there is a programmatic way, just given a link, of being able to do what we're doing now, fully automated. Just know that that exists. So the steps we want to take for this, we're going to open this up. Okay, that works too. Yeah, so what was just posted there, yeah, you're fine. Someone is trying to post the programmatic way of doing this. It kind of looks like this. I'll fix the issues here in a second, but this is good. Okay, so we can right click it, and well, I guess in Jupyter, it doesn't like it when you right click. So I had a file downloaded. I'm going to pull it from my browser, and I'm going to drop it into the bay. All right, here it is. We can see it again. Okay, so we have our data. What would have happened if I'd ran this is that this file didn't exist, and it would have given us an error. But now we can. All right, we have our data. And just so things are super clear, I'll put these here so that we can remember what our libraries look like. Okay, so the same kind of thing I was asking before. What kind of thing is our data variable? Obviously, it's a variable, but what is it? Is it a string? Is it a list? Is it a set? Is it an integer? We're using pandas to make it. Yes, it's a data frame. Okay, so we got our data frame. What's the next step? Remember that the question well, I suppose that that bears repeating. Why are we bothering coding if we don't know exactly what we're trying to ask? What questions are we trying to ask? We're talking about, what are the column names we have? Set A and set B. Set A versus set B. I'm doing some stuff with them, but what is that stuff? There are at least 3, depending on how you go about it. So what's the first thing we might want to ask about set A versus set B? These are the things we just did for the first exercise. So you can feel free to scroll up or tell me to scroll up, but we need to fill in this list before we do anything else, because it doesn't really help us to start coding until we know what we're trying to code. If you can't explain what you're trying to do in English or whatever language you're talking before you start coding it, then you're probably going to run into some problems. So we need to be able to do that. Anyone can answer, by the way. Your services are reset. What are we trying to do other than doing a lab on a Thursday? We need to plot the sets. Plotting the sets is a step on the road to what we want to do, but it's not actually the end goal. It's a good answer, because let's say I want to go to the store. Me getting in my car, me leaving, opening the garage door, getting in my car, and driving off is a step towards me going to the store. Additionally, finding the mean and the standard deviation are a good step on the way. Yes. If you are at all confused, you can look at the English description and the stuff above. So Dylan's comments are, so something Dr. Cleveland just said is the scaffolding of how things are going to work. What we have is a task, right? And we have step 1 and maybe step 1.1 and step 1.2 and then step 2 and so on and so forth. Dylan's comments are step 1 and step 2, which is great. We're going to need that answer. But the question I'm asking is, what's the task? What's the overall task? So Mark said to find out if the data sets are different or similar. Yeah, that is actually the overall task. Are these data sets, I will use significantly different or not? That is our, at the end of this, that's the null hypothesis we want to test. All right. I think, is it this? No. Maybe that. I don't know. Yeah, okay. All right. So that is the overall thing we're trying to figure out. What's the first thing we want to do? Not like reading in the data. We're reading in the data to do something. We want to know something about set A and set B. Are they something? Do they have a property? What is that property? Determine if the data sets are normal. Exactly correct. Determine if A and B are normal or not. Okay. What are we going to do after that? If normal, well, let's just say, I think it works this way. If not normal, choose other tests. If normal, okay, so determine if they came from the same distribution. That's really close. Exploratory data analysis will be to make the 2 plots. I think this is step 2, then proceed as you have listed. Okay, that's fair enough. So the answers were determine if the sets are normal, determine if they came from the same distribution. Yep. The steps we did above to answer that is we made some random sampling to see if that's good. All right. So this is good enough of a scaffolding to start coding. We've already started on reading in our CSV into a data frame. Okay, now what do we want to do with that data frame? Well, let's refresh what we were talking about. I enjoy the Socratic method as much as everyone else. Actually, probably infinitely more. But I don't want to spend 30 years trying to, as I am known to do. So what I'll do here is I'll say what's going on. Read our data into data frame. Get the columns out, separated out. Get mu sigma for columns. Random the sample with mu1, 2 and sigma 1, 2. Yes, copy and paste. And then we're going to plot. No, actually, no, we're going to make a new data frame to plot. All right. So employing the miracle of cut and paste. we're going to go to where we were coding. And the nice thing is I could erase all the code here. And I still have the English description of what I need to do, which is more than half the battle, as you will. Once you get, so I'm sure that this is a freshman class. I'm sure that you feel that the coding part is the uphill battle. And you're not wrong, because this is something you're learning. The language is something you're learning. But once you have the syntax and the directions of what documentation do I look at, you're going to realize that 90% of the work is this part. That's why I spend so much time on it. All right, so we're going to read our data into the data frame. Okay, well, as someone just pointed out earlier, this is the code to do that. Then we want to get the column separated out. Do I need to change anything here? Doesn't look like it. Maybe, maybe not. We have our data frame. We have our data frame here, same name. This is the variable name for our data frame. And we're accessing column set 1 and accessing column set 2. So does the $1 million question, does this, do these two lines, do anything need to change here? It's not really $1 million question. It's more like $2. Interesting. Won't work. Need to set them to set to A and B. Set A and set B. I believe Cole is correct. The thing we're trying to do here is exactly the same. But as you can see, the way the column names are different in our two data. And the way that Panda, I guess this will be NumPy, is working, our data frames work, is that you need to specifically use the name of the column. So it's set A, SET space A, and set B. So this needs to change a little bit. And I'm going to change these so that they are congruent. And then that. Okay. Now that that's all done, unless I made
You're
a,
missing the set B
I probably am. BS.
where it equals you.
Yep. Good catch. Good catch. All right. So let's see what that gets us. Well, it gets us a data frame. And what is this new data frame? Well, it's our randomly sampled, respective for set A, a random sample on that, and set B, a random sample on that. So what do we want to do with this? Well, we want to plot it so that we can see some stuff that goes on with it. And once again, copy and paste to the rescue. All right, what do we need to change here? Well, data 2 is the name. Probably should have, it doesn't matter. Let's see. So data 2 and data are now our new E2 data. They're not anything from before. And do we need to change anything else? I can change this. We don't technically need to, but it will reduce confusion. So the only thing I changed is the text in the title. All right. Now, what we're seeing here is the same kind of thing we were looking at before, which would be this. So we had 2 sets of data, set 1 in green, set 2 in red, and our random samples in blue and orange respectively. You could see that they were pretty close. The only particular thing I notice here is I can't see anything from blue or orange. And unfortunately, I don't know how to make one in front of the other. But what I'm guessing is Oh, there's an orange. Saying to change alpha to 0.5. Okay, let's try that. Where is alpha? Oh, it's probably another argument. So I just spent, I don't know, a second and a half, which is an eternity in brain time, looking for the alpha key on my keyboard. Don't recommend you do that. All right. So I'm going to do the same thing. Oh, yeah, I'll do the same thing up here so that I can illustrate a point. Or try to. And it's a period, not a comma. All right. So what we had before is you can see with the transparency now, the overlaps, and they look pretty close. Look at what we have here. Would you say those are close? Just visually? They are so unclose that I'm checking to make sure I didn't make an error. Okay, well, step one is we're getting there. Plot with random samplings together. All right. So we're done with this part. Now let's see if they're actually normal. How did we do that before? Well, we ran some tests. Oh, also we have the box plot thing, which is nice. We ran some tests. What test did we use? Well, we have a test that tells us if a distribution is Gaussian or not within a certain tolerance. So we're going to do that. First, I'm going to, I suppose it doesn't really matter, does it? Set A, set A, set B, set B. Okay. Okie doke. This one looks a lot nicer. Which brings up the point that there's not, that visuals can be misleading is the thing. Because according to this, the ranges in set B and set B's random sampling, they're not that different. The quartiles are very close. Same, pretty close with set 1 and set 1's random sampling too, or set A. So this graph looks real different. This graph makes them look pretty similar. But that is the reason we have the tests, because visuals can be deceiving. So copy and paste. We're going to see, is this data set actually normal or not within a 95% tolerance? It's probably normal. Okay, let's do the same thing for set B. Oops. Go. Set B, probably Gaussian. Okay. Well, we could have probably guessed that from the shape they look, but it's good to know for sure. So the next thing is to see if the data we have and the random sampling are from the same distribution. Here's the one that this one made it look like, probably not, but this one makes it look like probably. Now to answer the actual question, we use a test. All right, set. Nope. A. What did we call it? That. All right. Oh, I don't think I reran the. I am missing something somewhere. The error is saying set A underscore S is not, oh, is it capitalized? No, there's just no underscore, right? Ah, so remember earlier when I was saying that the column names needed to be changed? Well, I forgot my own advice. All right. And still, it's not capitalized. All right. So that's the first one. And this is the second one. B. All right. So our, I believe this is the Whitney test, tells us that set A and its random sampling are probably from the same distribution. And we can infer a little bit from the rejection, or the rejection threshold, but we failed to reject our null hypothesis. And our null hypothesis was that they are from the same distribution. Okay, so what have we done? We've collected our data, visualized it a little bit, determined they're probably both normal, determined that they probably both lined up with the random sampling we did. So what's the thing left to do? Well, we wanted to see if that set A and set B are significantly different or not, and significantly being the key word. And I'm going to do set A. Wait, no, it's not the right one. Ah, this is what I wanted. Okay. Okay. We're going to test set A and set B to see if they are significantly different or not. And our test, the Mann-Whitney test, says they are probably different distributions, which both of our graphs seem to really confirm. We're talking about the original sets. So the light green and the red, and that's comparing that one and that one. So no shock there. Let's see if the random samplings are different. That would be this one and that one. Probably different. Okay. Is that everything? Looks like it. So what did we reject, or did we fail to reject our null hypothesis? The null hypothesis was set A and set B are not significantly different. We rejected. They are significantly different. That is correct. All right, let's look at another example. So we've got a data set containing marks obtained by students on basic skills like math and language skills. It's collected from an educational institution. We've been tasked to give them some important inferences. Now, right off the bat, this is when you study the normal distribution, what is it? This is one of the examples. Like grades on tests are almost always normal, but we don't know that for sure. The hypothesis we want to test is there is no difference in the means of student performance in any of basic littering skills, i.e. reading, writing, and math. So if I'm reading this correctly, take the performance in students on average in reading, writing, math, and respectively, there's no significant difference in any of them. Okay. So we've got the data. It's on the web root. Here is the automated way I was talking about earlier. What this will do is everything we did with drag and drop, but we don't actually have to drag and drop. All right, so now we've got our, once it says idle, that means you've actually got it. So we're gonna do everything we did before. We're going to make a data frame. We're gonna use the head function so that we can see some parts of it. What's in our data frame? We've got gender, ethnicity, education of parents, lunchtime, the preparation course, did they complete it or not? And then we have their math, reading, and writing scores. All right. Someone says they get an error / warning for Seaborn. If it's a warning, and I believe I got a bunch of warnings, you can just ignore it. It's just that I cleared all my outputs, and once the warning shows up once, it doesn't show again. So I think if you clear your outputs and run it again, you should be fine. But if it's a warning, you could just ignore it. All right, we're also going to use the describe function, which is what I was talking about earlier. One of the nice things about the data frame is it tells us the 5, and I think this adds another one. I don't remember which. It might actually be missing the mean. No, it's missing the mode. Not important. But what it does tell us is that for all of them, we have 1,000 entries. The mean for math score is about 66. The mean for reading score is about 69. The mean for writing score is 68. Standard deviation for each. We got the minimum, the quartiles, and the maximums. So really, if I am being tasked with doing this, the first thing I think about is, okay, well, here's where the real answer is going to be lying. Really these two, but this one is the big one. Is the difference in 66, 69, and 68, take any of those, and the biggest one is going to be 69 and 66. Is that significantly different? That's the question we've got to answer. So how are we going to do that? Well, first thing, let's get the data out of the columns. So we're going to have some series for the math, reading, and writing. Got them. And we'll use Seaborn again. And yeah, here's my warnings. And what we're going to do now is we plot them all on top of each other, both with the histogram and an actual line, to see if they're similar-ish. How similar are they? Don't know. Well, from a visual inspection, it's pretty similar. If we were to see something like this, definitely different, but based on what we've got, looks pretty similar. So once again, visuals can kind of give you a hint of where to go and what questions to ask, but it really won't tell you. So let's do the tests we need to do. What is our null hypothesis? The null hypothesis is there is no difference in performance of students between any of their tested skills. There just so happens to be 3 on this exam. There could be a bunch. The alternative hypothesis is there's at least one difference in performance of students between math, reading, and writing. So if I had 100 skills that I tested, the null hypothesis is only true if there are no 2 tested things that are significantly far apart. So we're going to do the same test for every pair we have. So we have math versus writing, and reading versus writing. This is an interesting formula called in choose 2. Yeah, so it's worth pointing out. Open source has a bunch of benefits, more benefits than drawbacks, otherwise we wouldn't use it. One of the drawbacks is because it's open source, function names can change, or rather, this function does a task, but in development is a new function that does the task better. And it's different enough that they need to make the old function no longer usable. So after a couple versions, it's not going to work anymore. we're in the period where it still works, but the new function is what they're encouraging people to use. But you don't need to worry about that. Just know that it's a thing. Okay, we're going to test each test. Can't quite call that a pun, but it is interesting. Test each test versus the other ones. Set 1 versus 2, set 1 versus 3, and set 2 versus 3. Okay, are these the same distribution? Probably not, according to Whitney. So let's see, this is math versus reading. This will be math versus writing. And this will be reading versus writing. So when we were looking at before, remember I was talking about the mean? 69 versus 68 is less of a difference than 69 versus 66. One way to look at that is if these two are different, then you are guaranteed that these two are different almost. And by different, I mean from a different distribution. So our tests tell us that the 66 versus the other two means that it's probably from a different distribution. It's hard to say. But it also says the same test that the 69 reading versus the 68 writing are probably from the same distribution. This one actually came pretty close, which is probably why it's the exercise. Okay, now we're going to use our Kruskal test on all three of them. So this test, again, black box, you just need to know what's the input, what's the output. The input to this test is a set of distributions, and the output will be a rejection or a failure to reject of are they all from the same distribution. This one tells us, and my gut is telling me that the way this test works is it just did what we did here for each pair. That with a 95% confidence, the three we put are probably different in at least some way. Okay, so that's another from problem to, I guess it's not a solution, it's a answer to the question, are these different or not? Example. Let's see. I think, let's look at the homework before I try to go through that example. So the homework, you're going to be doing a lot of what we just did. Remember, it's really, I wouldn't say easy. It's really important that you type out what you're trying to do, just like a list of tasks before you start coding. So we've got some data. It's the impact strength of packaging materials in foot-pounds of two branded boxes. Produce a histogram of the two series and determine if there is evidence of a difference in mean strength between the two brands. Use an appropriate hypothesis test to support your assertion at a level of significance of alpha is 0.10. Now, what does that mean? Well, we're essentially answering the question of the resistance to being bashed on Amazon boxes versus Walmart boxes. Are they different or are they close? How different are different? That question's answered for you right here. This is extremely helpful. So make sure to make use of this when scaffolding is already given for you. That's awesome. Okay. So if you remember that's really all there is to say about the homework, because what you need to deliver and some hints are already given for you. The last thing I will mention about the homework is remember the 4 steps I was talking about? This is one of those instances where you don't know which test you want to use. So you need to, and remember, You can probably watch the recording. I won't mention it now because it would give away too much. But there is a process for choosing the right test. So think of that process and think about the situation you're in, so that what question am I trying to answer and what kind of data do I have? Those are usually the things you want to know. And I've probably already said too much. So that's that for the homework. It's do everything we've been doing in the lab for some new data. All right. There's another example here, and I like the end of it because it reminds me of a John Carpenter film. We have two different kinds of fonts. Well, really, we have a client considering switching to do different from one font to the other. The question is, so we're like a firm that answers this question. Newspaper's coming to us and is saying, is this going to be more readable or not? The fonts they're considering are Times Roman and Times New Roman. The difference is subtle. I believe these are called serifs. It's been I don't know a whole lot about it, but as you can see, there is some difference in the font. They want to know, is one of these significantly more readable, statistically significantly more readable for audiences than the other? If so, they want to swap. If not, they don't want to waste the money. They prepared some samples and they did this, they collected the data for us. They went out and randomly gave half of the people one version and the other half the other one. And then they see how many people from those two, I guess they're from the same sample, but from those two groupings actually purchased a newspaper. The number was 175 for the first one and 200 for the second. Based on the observations of the first day, first, we need to calculate the purchase rate for each group and then decide whether the client should change their font in order to increase their sales. All right. So day one, they had a way of splitting everybody into two even groups. Don't know how they did it. We're assuming it's just a fair way that it went. Could have drawn lots. Who knows? We have the number sold for group one, the number sold for group two. We know the rates, just the number divided by the group size. All right. So we have the rate and we have the test that's appropriate for telling whether one is better than the other. So that test tells us that the probability that group two is, what was the, so group two had the new theme. Okay. So the likelihood that the new theme increases the purchase numbers with a, oh, this is an interesting way to do it. Instead of saying with a % confidence, we're saying that the likelihood that one is better than the other is 93%. That's pretty good. So they ran, that was just the data for the first day. After a week, they did the same thing. And now that we have more data, we run the same thing. Now our test is telling us that the new font is better than the old font with a probability of 99%. They kept running the experiment for a month. And here's the data they collected. So we went from a one-day experiment telling us 93%. Well, the client wants to be 100% sure. You try through a conversation that lasts about 20 minutes and some whiteboard stuff that can't really be 100% sure. They don't listen. So they run it for a week and you tell them, well, look at this, I can get you 99%. And they say, that's not good enough. I got to get 100%. At this point, you realize that they're never going to understand entirely. So you list out an absurd amount of decimals to the point where you can say, yep, this is 1.00000 for this amount of decimals. You say under your breath, and then they're satisfied And now you have an answer. And then this reminds me of they live. Okay. So that is 3 different. You've got some data, you've got a question. What do I do with it? Examples using Python. And you've got a 4th. That's the homework. The question is, given this data, is one box brand more smash proof than another with a level of this? And that is pretty good timing. So that is all I have. I will
reclaim the host.
Yeah, that's what I was trying to find.
And turn the video so you can see my charming face. Thank you everybody for your attention. There weren't too many of you, so you guys should have a pretty good edge when it comes to our 3rd exam. The homework assignment is straightforward application of the contents of lesson 16 in this lesson, lesson 17. So you should be able to find enough bits of code to cut and paste to be able to do the homework. And with that, I'm going to stop the recording and hang up on you all. So everybody have a great day and a great weekend. Bye-bye.
See you guys next week.